Focus. Okay, hi everyone. So today we're working on the next step. We talked about inequalities as being more than one solution, a range of solutions. Now we're gonna go the counter way and say only one solution now. And this idea here is we're going to solve a system of line equations by graphing. Now I'm going to say this is our last section. Normally, before the end of the semester in a regular school year, we would cover this and the different methods of doing this algebraically. But since we are running out of time, this will be our last section, our last new section. The rest of the classes will be meant for review about graphing lines, about solving equations, order of operations, how to work backwards, how to read a problem. So this is really our last new section. Hooray! Fireworks, illegal fireworks now. Okay, so we're going to talk about what we're talking about when we say solve a system of equations in a more, I guess, realistic sense, and then how to look at it in a graph. Okay, so here's the idea. You have a family full of people, mother, father, maybe grandmother, maybe brothers and sisters, and you guys all have your own lives, right? And you guys all have your own schedule. Have your parents ever come in and say, hey, we're going here now? And you're like, wait, I'm busy. Or, hey, we're going to do this. And you're like, oh, man, I wanted to do this, though. And with conflicting lives, right, it's hard to find a point where you guys can all get together. Especially now with restrictions where we can't meet in big groups. So here's the idea, is that if I look at my graph here, and I have a line graph. That's one line graph. So we'll call this George. And we have another line graph. We'll call this Mary. At what point would George and Mary meet up? I'll give myself some tick marks. Okay, 1, 2, 3, 4, 1, 2. At what point on the graph does it look like George and Mary will actually meet up? Does it look like they meet up at a lot of places? Do they share a lot of points together? Now, what I mean is, if I pick a point here, this is Mary, right? But George is over here. They are not in the same spot, right? So George and Mary, for them to agree to be at the same location, they have to share a common point. And if you probably notice this, but the only point that they share is where the lines intersect, right? And this is where they intersect. And at this point, both George and Mary have the same GPS coordinates. They have the same coordinates. And the coordinates are 4, 2. They intersect at 4, 2. So this is our idea right now of solving a line system of equations, saying, hey, you have your life, you have one line equation, you have another line equation. And at what point do they both meet up? Like, really? Like that's what we're doing here. We're going to graph two lines, and then we're going to figure out at what point are they going to intersect, and that is a solution. That is an answer to both those equations. Okay, so let's go ahead and do an example of this. Let's say y okay. Let me give you. Let's look for another one. Okay, so here is my equation for you guys. Y is equal to x minus 2, and y is equal to negative x plus 6. The great thing about this problem is that this is already in a very graphable slope-intercept form. And our slope-intercept form is y equals to mx plus b. So make sure you know what the m is for each of these equations, as well as the b value. And this will, you don't always have to write it, but it does help if you know what you're looking for, right? So my slope here is an invisible 1, so 1 over 1, and my b value is negative 2 for my first equation. My second equation is negative 1 over 1, and my b value is 6. So I want you guys to right now, okay, answer this question. Do you know by looking at these equations Yeah, y equals to x minus 2 and y is equal to negative x plus 6. Yeah, I know where they meet. Like hell you know where you meet, right? So in a sense, like us trying to go to a new location and us not having a clue where it is, we're going to pull out a map. And we're going to lay down a map. We're going to lay down some directions. Let's go ahead and draw our little map here. This is going to be our x and y plane. X and y. And one of the most basic ways of figuring out where lines meet is by graphing each of those lines. So let's graph the first line. We'll do this in, let's do this in red, and then we'll do this in black, okay? Red and black. So in red, the y-intercept is -2, high -2, put a dot, and the slope is 1 over 1, so rise 1, run 1. Rise 1, run 1, and I'm going to draw a line something like that, a little off. So the problem is you want to draw a line as best as possible, as straight as possible, making sure all your tick marks are perfectly balanced, making sure that the world is at peace. And we know this is very hard for us to do sometimes. Even with a ruler, you might be a little bit off. And now this is the problem with graphing. Your graph and my graph aren't always going to look perfectly alike. Maybe it's a little more skewed than another, right? Because we're just humans. And the next part is lines don't always meet exactly in a nice place, especially when my lines are crooked. So I'm going to try my best to keep these lines straight, keep my lines apart. And I'm going to go ahead and graph the second point. We'll use black now. The y-intercept is 6, so 1, 2, 3, 4, 5, 6. I'm just trying my best here, trying my best. And that is 6. And the slope here is -1 over 1. -1 over 1. Okay, I'm hoping that looks about right. Now, you see that these points do meet. All lines will meet. Okay, all lines will meet except for parallel lines. Actually, that's the only time lines will meet. When lines are parallel, take a look. They go heading in the same direction, right? Parallel lines will never intersect. So whenever you have parallel lines, there's actually an answer is no solution because they will never meet. It's like, imagine Romeo and Juliet were living parallel lives. They would never have met each other. No solution. Okay. So let's go back and try to make a guess now. Where do you think this point is? What would this point be? Okay, so I'm going to draw a couple more tick marks. 1, 2, 3, 4. And this looks like 2. Take a look here. Does that look about right-ish at 4, 2? Meh, yeah, meh. Not bad, right? So my x value is 4, and my y value is 2. And that's my guess right now. If we were graphing this on a computer, you know what? We can do that. Let me go take this to Desmos, because Desmos is cool. But Desmos doesn't help me learn anything. He just kind of graphs it for me. Let's take a look at Desmos. If I write the question y equals to x minus 2. Okay, that's my first graph, which is what we had drawn. The second graph will be y equals to negative x plus 6. As we can see, the line intersects like ours also did. And let's take a look at what Desmos says. And Desmos says 4, 2. Does our graph look kind of like that? Back and forth? Yeah, that's not bad, right? Looks pretty darn close. Now, did your lines meet at 4, 2? And here's our problem. Is that graphing without, let's say, a perfect environment, perfect lines, perfect dashes, perfect spacing, might lead us to answers that are a little bit off. So what does 4, 2 mean? It says this is the answer that would be true for both equations. So let's test those equations. For my first equation, if y is 4 and x is 2, I messed up. So x is 4, y is 2. I flipped that around. 2 is equal to 4 minus 2. Is this a true statement? 4 minus 2 is 2, and 2 is equal to 2. Yes, 4, 2 is a point in line 1. Okay? Okay for line 1. Let's check the other point. To check the second problem, 2 is equal to negative 4 plus 6, right? We plugged in the x is 4. Well, that's 2 is equal to 2. And yes, this is also true. So guess what? They both share a common point at 4, 4 comma 2. Have you ever texted a friend and then you're like, oh yeah, I'm at the mall. And your friend's like, oh, I'm at the mall too. It's like, yeah, I'm in front of Gap. I'm in front of Gap too. That's kind of what's going on here. You guys are sharing the same point. In this way, in this sense, you have the same time and the same place. Maybe it's 4 o'clock and we're at the store number 2. So we're both at the same spot. We're intersecting here. And this is one solution that we can say we have in common. When you're trying to meet up with friends, you say, hey, are you available at 3 o'clock? I'll meet you at the mall, right? You're trying to find a common place to meet and a common time to meet. Your parents will say this if you guys are at the mall already. Hey, we're going to meet in front of Macy's at 3 o'clock. Okay, Macy's at 3. So that all your lines as a family will eventually intersect back and have one solution. And this is what we're looking for. We're trying to find that point where they intersect. And that point is a solution that they both share. All these other points are not points that are in common. So they're not solutions. So let's go ahead and try another problem here. So this one is going to be a little harder to draft, but let's try it. Y is equal to 5x and y is equal to 2x minus 3. Okay, this is a different graph. I'll use black for here and maybe we'll use red for the second one. Okay. So let's go ahead and graph these two lines. We've been practicing graphing lines already. A couple of things to take note. What is the slope and what is the y-intercept? What is the slope and what's the y-intercept? Remember, these are our two key components when it came to graphing in slope-intercept form. The y-intercept is nothing, so that's going to be 0, and the slope is 5. I'll say 5 over 1 to make my graphing easier. My second graph is negative 3 for my y-intercept, and my slope is 2 over 1. Okay, so this should be something that we are well versed with already. If you're not well versed, if you're still confused, we're reteaching it right now. Okay, so let's go ahead and graph these in red. My y-intercept is 0, so graph is 0. And the slope is 5 over 1. So let's try to do this the best we can. 1, 2, 3, 4, 5 over 1. I'm going to graph the line the best I can. I could probably use a ruler, right? But you guys don't have a ruler. If you need a ruler, you can take out your ID card. Any card you want. That could be a what we call a straight edge. I could have taken out my ruler. See? We're good on that. Alright, so let's go ahead and graph our second line. We said that's going to be in black. And the y-intercept for here is negative 3, negative 1, negative 2, negative 3. And my slope is positive 2 over 1. Positive 2, rise 2 over 1. Rise 2 over 1. Okay, rise 2 over 1. Sorry, I was at negative 3, right? Rise 2 over 1. Rise 2 over 1 if I want to keep going. And we have a line here. Now, if you look at this, the line's not going to meet in front. I mean to the right. See, it's not going to meet over here. But it's actually going to meet in back. And it's going to meet someplace right here. Now, what is that point that's going to meet? Now, we could look at my ugly graph and say, no, that looks like, I don't know what that looks like. That looks like that's a negative 1. And maybe it's going to be 1, 2, and that's going to be negative 5. This is negative 3. Maybe negative 5. And you know what? Maybe that's it. But here is a trick that you can use when you're graphing. count the slopes. If I go down 2 and I go back 1, hey, that looks about right. Down 2, back 1. If our answer is a whole number, definitely that will be helpful. So what is down 2 from 3? Negative 3 down 2 is negative 5. All right, that looks like it's negative 5, right? And if our y-intercept is at x is 0, 0 minus 1 is negative 1. This is our y's and our x's. So does this point look like negative 1 comma 5? Oh, negative 5, negative 1, negative 5. Let's see if that works. Let's see if that works. So for my first equation, let's plug it in. Does negative 1, negative 5, is this a true statement for both the equations? Y is equal to 5x and y is equal to 2x minus 3. Let's go ahead and check it to see if this is a true statement for both these. We're going to plug in our x's and y's. Negative 5 is equal to 5 times negative 1. How did I do that? Because y is negative 5 and x is negative 1. Just rewriting this. A big deal about math is being confident in rewriting. Plug in and rewrite. On the right side, negative 5 is equal to 2 times negative 1 minus 3. Negative 5. 5 times negative 1 is negative 5. Okay, it worked for my first equation. That's a win. Does it work for my second equation? This is negative 5 equals to negative 2 minus 3. You owe me 2, you owe me 3. You used to owe me a lot of money. You owe me 5. And yes, that is also true. So we verified my crappy graph here by just plugging in the number to my equations. And if they both have a true statement, they both have a common point, yes, these points intersect at that one point. And we call this a solution to the system of equations. And the solution is negative 1, comma, negative 5. So why do we even call this a system of equations? Well, the idea of a system, it just means it's more than one. Like think of your computer system. You have a monitor, a keyboard, a mouse, a CPU hard drive unit, okay? A computer system made up of many components. A solar system is made up of more than just one planet, right? So in our solar system, we have a sun and 8 planets, and Pluto is a planetary body or something like that. So we say a solution to a system is there one answer for them all? Is there one answer for them all? And in some cases, there are no answers. So there's only one time, as we mentioned before, that there's no answers. No solution if lines are parallel. So I'm going to ask you right now if there's a solution for this next set of equations. 3x plus 2y equals to 6, and y is equal to negative 3 over 2x minus 10. Okay, I want you to take a look here and tell me, will there be a solution for these two lines? Will they ever meet? If I go ahead and solve for y here so I can make this graphable, we can minus 3x to both sides. 2y is equal to negative 3x plus 6. If then I divide by 2 to everyone, y is equal to negative 3 over 2x, and 6 divided by 2 is 3. Hey, now I can graph these if I want to, but even before I even graph it, I can realize that negative 3x make these lines parallel. Lines are parallel. So if they're parallel, that means there's no solution. Why is there no solution? A solution is an x and y point that both lines have. They both have that same x and y point. Imagine if anyone ever track your iPhone and it tells you the GPS units, and the last time the GPS read the location. That's kind of what we're doing. We're seeing, do these have the same time and place, x and y? But when they're parallel, let me go ahead and graph these now. 1, 2, 3. The slope is negative 3. 1, 2, 3 over 2. That's one line. Next line was at negative 10. Negative 2, 3, 4, 5, 6, 7, 8, 9, 10. And then the slope was negative 3 over 2, negative 1, 2, 3 over 2. These lines here are parallel, so they will never intersect. No matter how far you go, these lines will never meet up. They're like train tracks, right? Train tracks are always parallel. Sometimes you see them cross, but it's because they're changing lanes. Okay, but they're always parallel. If train tracks crossed like that, your train would just derail. Okay, so if we can tell that lines are parallel, we can automatically say there is no solution. And the answer is no solution. If someone says, hey, did you meet up with your friend? Answer is no. Because if you guys don't have the same common point and common time, yeah, you didn't meet your friend. Okay. So, what if I don't want to graph? On IXL, they're going to ask you some questions, and the question is going to be, hey, is this a solution for the system? So if I give you y is equal to 2x plus 4, and y is equal to x plus 2, and then I follow up with, is negative 2 comma 0 a solution for the system? We could graph it, or if we're just checking, you just have to plug in the x and y. Just plug in the x and y to each of these equations to see, are you a point that works? So let's go ahead and try it. 0 is equal to 2 times negative 2 plus 4. And on the right, 0 is equal to negative 2 plus 2. What I did was I just plugged in x for x and y for y. X for x and y for y. And 0 is equal to negative 4 plus 4. Yeah, negative 4 plus 4 is 0. 0 is equal to 0. On the right, 0 is equal to 0. Yep, this is true. Turns out that negative 2, 0 was a common answer for both of them. Okay, so you don't believe me, right? We tried plugging the points. Fine, that's graph it. That's graph it. You convinced me, guys. Everyone, you guys convinced me to graph it. 1, 2, 3, 4. That's my first line. I'll do the first line in, let's call it blue. That's blue. And I'll do the next line in red. So in blue, the rise is 1, 2, and the run is 1, 2 over 1. Okay, the slope is 2 over 1. The y-intercept is 4. And we're going to go ahead and graph that line. All right. The graph is a little terrible, but sure. And then the next one is y is equal to 2 with a slope of 1, up 1 over 1. Okay. So if you look at my crappy graph, does that look like negative 2, 0? It looks a little off from that. So the issue about us graphing, especially if we're not taking care to make the right tick marks and everything, is that we're going to get an answer that looks really off. And that's the flaw about graphing. But it's the process that we're going to do right now. It is one of the easiest ways for us to start having a conversation about the answer to a system of equations. If they graph and they intersect, that is the answer. But of course, our lines have to be nice and pretty. And in this case, that more looks like maybe 3 or 4, negative 3 or 4. So I'm going to draw this one more time. I'm going to take a little more care. 1, 2, 3, 4 over 1. Okay. So 4, 5, 6, let's say 6 over 1. So these are my 2 points. This is 4, and then rise is 1, 2, and run is 1. Oh, probably should have done that a little bit lower. And I will make that look a little better because I don't want to get an answer that's really off again. Okay, use my little nice ruler. And then we'll use a one in red. This is 2 over here. And the slope is 1 over 1, so up 1, over 1. Okay. Yep, missed that one. Okay, that looks a little bit better. Looks for kind of similar to what I did before. But the tick marks, I still missed, right? I still missed. But it was still pretty close, right? And that's one of the problems with us graphing is that we're not surgeons here. We're not perfect in every way. So our graphs will always be slightly off. And that's because of us, not because of the math.